Well, hello everyone, and welcome to this afternoon's CMCC webinar. Thank you all who are already here, and I'm sure more people are coming in the door as I see now. So welcome to you all. This is a webinar on mastering tropical cyclone representation within the CLINT project. And we have not one, but two speakers today. The first is Leone Cavicchia, who is a scientist at the Climate Simulations and Prediction Division at the CMCC, who has 10 years of experience on climate extremes and modeling, which includes studying tropical-like cyclones in the Mediterranean, the so-called medicanes, as well as subtropical cyclones in Eastern Australia, where he spent 3 years as a research fellow. He's been involved in a range of international and Italian national research programs, and at the moment is currently focusing on AI enhancement of tropical cyclone representation. After Leone, we will have Guido Ascenso from the Environmental Intelligence Lab at the Politecnico di Milano. He's a postdoctoral researcher with a PhD in applied deep learning from Manchester Metropolitan Uni in the UK. At the moment, he's focusing on deep learning to model extreme events, which of course include tropical cyclones. And his research interests and methods include computer vision, shortcut learning, and causality. So we will hear from Leone and Guido shortly. Now I'm going to introduce the CMCC, the host of this webinar. The CMCC is a center of research which covers a wide range of climate research and applications. So its mission is to investigate and model our climate system and its interactions with society. It's about protecting the environment, developing science-driven adaptation and mitigation policies in a changing climate. And one of the aims is to develop foresights and qualitative and quantitative analysis of our future planet and society. The CMCC is based around Italy with offices and divisions in the north, the south, the center, and including some of the islands. It's a network distributed throughout the country that also connects public and private entities working on multidisciplinary studies around climate change. We're linked to a range of universities and other entities, not just in terms of the research done, but also in the provision of teaching resources and education at the universities, and in the maintenance and planning of many PhD programs, which are done in collaboration with these universities and the CMCC. As you can imagine, it's all about interdisciplinary research. So there's a range of divisions, as I've mentioned, from scientific computing to climate predictions to sustainable economic modeling, et cetera, and there's a lot of crosstalk and crosswork between these divisions, really making the most of these interdisciplinary skills which are found throughout the CMCC. We also are home to a supercomputing center based in the University of Salento campus in Lecce, which has been operational since 2008. It's the only computational facility in Italy specializing in climate change research. And it's currently building a new center we're currently updating, which would include the upgrading of computing and storage facilities. And here on the right, you can see some of the statistics about this supercomputing center. It really is state-of-the-art and powers a lot of the innovative climate research done at the CMCC. Beyond that, the CMCC is very much involved in outreach. So going beyond producing scientific articles for international journals, we're involved in educational programs, events, communication, and other dissemination activities, like, of course, this webinar and many others in this series. Now for a bit of technical detail about this Zoom call. Currently, all the attendees have their audio and video deactivated by default. If you need to intervene or ask questions, there are specific ways of doing that. At the bottom of your screen, you will see the Q&A section, which I encourage all of you, as many as possible, to write in and ask questions to our two speakers. You can write them throughout the call and they will be answered at the end. Alternatively, you can use the raise hand feature, and when we get to the question and answer session at the end, I will be able to give you the floor. Finally, before we get going with the main content of today, there's a few final remarks. So this webinar will be recorded and uploaded on the CMCC YouTube channel, which you can see there. And if you have any further questions about the webinar, you can email the specific webinar email address. Lastly, don't forget to follow us on social media, on Twitter, on Facebook, etc. It's at CMCC Climate. Do it after the webinar, because for now we're going to be focusing on the first of the two talks today. So now I'm going to stop sharing. I'm going to pass over to Leone, who will begin with the first half of the webinar today. Leone, I hand over to you.
Hello, good afternoon, everyone. Thanks, Ronan, for the introduction. Let me share my screen. Can you see my screen?
Not yet.
Okay. Okay.
There it is.
Working now? Yeah. Okay. Okay. So together with Guido, we will show today some of the results of the research that has been performed in the CLINT Horizon 2020 project, which is dealing with the improvement of the detection, prediction, and attribution of extreme events with artificial intelligence techniques. And in particular, today we will be focusing on tropical cyclones. And in the first half of this webinar, I will introduce the topic of today's talk, which is tropical cyclones. And I will show you some of the traditional methods that we use to characterize these kind of storms and their occurrence, and also some of the limitation of these traditional methodologies. And I will then pass the floor to Guido, which will show some new methods that we have been developing in the project to improve the representation of tropical cyclones. So just to introduce the topic of today's talk, which is tropical cyclones, I've chosen to start with a few pictures and information on the very last big cyclone that has been happening just a few weeks ago in the southern Indian Ocean, which is tropical cyclone Freddy. You might have heard about it in the news. Here you can see just two satellite pictures of this storm, in which you can see I would say the almost perfect structure, textbook structure of the storm here on the left with this very peculiar shape with the spiral shape and the cloud-free eye in the middle. And on the right-hand side, you see the size of the storm in the moment where it's about to make landfall over Madagascar. And unfortunately, this storm, this cyclone produced a lot of damage in the countries in Southern Africa that were affected by its landfall, in particular in Malawi and Mozambique. And there were several fatalities, few hundreds. Probably this number is still temporary. And this gives a measure of the importance of being able to predict the occurrence of these kind of events as precisely as possible. Another aspect about this cyclone is that it's been a record-breaking tropical cyclone for many aspects. You can see here in the picture the track. So this cyclone developed close to the western coast of Australia at the beginning of February, and it crossed the whole southern Indian Ocean until reaching the eastern coast of Africa over a few weeks. And after making a first landfall on Madagascar, it crossed the Mozambique Channel and it made landfall over the coast of Mozambique. And then it had this very peculiar behavior. Instead of dissipating after landfall, it traveled back to the ocean where it gained energy again. And then it inverted the direction of propagation again, and it had the second landfall over the coast of Mozambique. And this very peculiar behavior made it the longest tropical cyclone ever recorded. It has the duration of 38 days. So the previous record was 30 days. So it exceeded this record by more than a week. It also seems that it has broken the record of the mostly energetic cyclone ever. So in terms of the quantity that's called accumulated cyclone energy, that gives a measure of how much energy is created and dissipated during the cyclone lifetime. It was the most energetic storm ever. It had alone accumulated cyclone energy larger than a typical full North Atlantic hurricane season. And this is just a couple of weeks from the storm occurrence, so maybe we will made aware of further records that are broken by this cyclone. And just give me 1 minute to show you this very remarkable video where you show the evolution. We see the evolution of the storm. It's the red bubble on the right-hand side. As I was saying, it's crossing the whole southern Indian Ocean with the very typical hurricane shape. Here it's making landfall over Madagascar, and it's crossing over to Mozambique. And it spends a few days there associated with very heavy precipitation. And then it travels back towards Madagascar again. It strengthens. It acquires again the structure of mature tropical cyclone. And here now it makes landfall for the second time over the coast of Mozambique, eventually dissipating. And oops. Okay, so starting from these very remarkable case studies, I've put together here just some basic information, general information about tropical cyclones. So the tropical cyclones develop over the warm waters of the tropical and subtropical oceans, from which they extract the energy that maintains maintains their evolution and intensification through deep convection. And because of the physical mechanisms involved in the sustenance of the storm, they develop this very peculiar structure with cloud-free eye at the middle, and rain bands characterized by very heavy rainfall and strong winds in a symmetrical shape around the center of the storm. And about the general occurrence of these kind of cyclones, this is a picture representing the climatology of all the tropical cyclones occur over the last about 40 years. So what we know is that on average between 80 and 90 tropical cyclones per year are formed across all the tropical ocean basins in the world. This number is quite stable, and remarkably, we don't have a theory to date that explains why this number is around 80 and not 8 or 800. Just keep in mind this fact, because it will come back in the following in this seminar. As I mentioned before, they have a radius between 100 and 2,000 kilometers, and they develop in all the tropical basins in the world, except for the South Atlantic. As I was mentioning, we don't have a precise theory of the formation, but we know some of the conditions that are necessary for these kind of storms to develop and intensify. So as I mentioned already, we need warm waters in the ocean that are a source of the energy that maintains the storm. But this is not everything. We also need unstable atmosphere, a lot of humidity, especially in the middle layers of the atmosphere, to support the convection and the mechanism that maintains those storms, and also low vertical wind shear. So there has to be a small difference in the direction and strength of the wind in different layers of the atmosphere. So this knowledge about the factors that are needed for cyclone formation are used to characterize the formation of those storms and to build these kind of indices that are used to describe the formation and occurrence of the cyclones in space and time. They're basically built in this way. There are several formulations. This is one specific example on which Guido will give you more details in the second part of the talk. So they're basically a product of different factors that are needed to the formation of the storm, and we can use them to describe some of the properties regarding where and when these cyclones are formed. As you can see, these indices are generally pretty good in reproducing the spatial patterns of cyclone formation and the seasonal cycle that is quite different from the southern to the northern hemisphere. And these indices were derived on these two quantities, so they are quite good in reproducing them. Given this, we would be very happy if they would be able also to describe not only the climatology of tropical cyclones, but also to be used to make some predictions about tropical cyclone activity, both in the seasonal scale and to estimate future trends. It is already known that these kind of indicators have some struggle in making this kind of prediction of the interannual variability of tropical cyclones and on the future trends. But we wanted to quantify better their skill in with respect to these two metrics, because one of the goals of our project is to improve these kind of indicators. So the first part of the work that we did was to compare the number of cyclones that is represented by these indices and the number of cyclones that are actually simulated in an ensemble of climate models, which was produced quite recently, a few years ago. It's the IRIS-MIP ensemble that is part of CMCC. And for the first time in this climate model ensemble, we have a high enough spatial resolution to be able to simulate the cyclones directly. So this first part of the study was the objective was to give some kind of benchmark of the ability of these indicators to capture the internal variability and future trends of these kind of indices in the IRIS-MIP ensemble. So, as I mentioned, we considered three slightly different formulation of those indices. They involve different combinations of variables with different coefficients. You don't need to get all the details, but they are more or less equivalent in terms of describing the spatial structure and seasonal cycle of these storms. And so we compare the variability in at the interannual scale and the future trends of these three indicators with the storms directly detected in the 5 models that are part of the IRIS-MIP ensemble. And you can see here a first summary of this benchmarking study. So here you see across the 6 main ocean basins of tropical cyclone formation, a measure of the correlation between the annual time series of the genesis potential indices and the directly simulated cyclones. These are the 3 indicators, which have some small difference, but the overall behavior between the 3 is quite similar. In a perfect, if these indicators were perfect, you would want to see a correlation of close to 1 between those time series. And you can see that this is quite far from reality in the model world. and the correlation is better in some ocean basins compared to the others, but overall it is quite low. And another thing that we were interested in looking at is how these indicators follow the projected change in future tropical cyclone activity. So here you can see the relative change in these three different genesis potential indices in the future simulations with respect to the historical simulations. And you can see that there is some increase, not huge, but still there is an increase over most of the areas affected by tropical cyclone formation, in particular here in the northeastern Pacific, and also in the northwest Pacific, you see the biggest increase. And again, when you compare in the model ensemble the number of tropical cyclones detected in the models with the number of tropical cyclones predicted by these indices, you see that the consistence between the two is not as high as you would like. So in a perfect world, you would expect all these points to cluster along a diagonal on this plane. So when the simulated cyclones increase, you would expect to see also an increase in the cyclones predicted by the index. But as I said, there is a consistency in some of the ocean basins and in the models, but not in all of them, at least much less than we would like to have. So there are, to close this first part of the presentation, there are a number of reasons why we think that these indicators might not be that good in reproducing the simulated cyclones. They might miss some ingredients, or there might be some flaws in some of the other methodologies that are involved. So we, together with Guido, we started to investigate new methodologies to improve this representation. And I will stop here and leave the floor to Guido that will show some of the results coming up from this project.
Thank you very much, Leone. As we pass over to Guido, I would just remind people that they can leave questions. I encourage people to leave questions in the Q&A section at the bottom of the screen. Guido, over to you.
Thank you, Ronan, and thanks Leone and everyone for joining us today here at this CMCC webinar. And I'll just pick right off where Leone left, discussing the limitations of these genesis indices. The starting point for our research in this task of the CLINT project was, as Leone was saying, to improve the performance of these genesis indices, especially as our starting point, we took the Emanuel and Nolan Genesis Index, which is a particularly well-known one and well-researched one. And this is that index. It was also in one of Leone's slides. I will go over very briefly what the inputs are. Don't want to spend too much time on this, but if there are any questions, feel free to ask in the Q&A section. But essentially, all the inputs are large-scale climatological variables, except for one, starting with vertical wind shear, relative humidity, maximum potential intensity. This is a derived variable. It's a combination of other variables that include, for example, the sea surface temperature, among other variables. And this gives an estimation of the highest intensity that the tropical cyclone is expected to achieve. And finally, absolute vorticity. And all these variables are taken at specific pressure levels or heights, so to speak. And as Leone was saying in his slides, in terms of spatial correlation, the index works fairly well. If we calculate the correlation between these two images, on the left, the index calculated on some reanalysis data, and on the right, the observed actual points of genesis of tropical cyclones over the last 40 years, the correlation is fairly good. It's about 0.6, meaning the index is good enough at capturing the spatial component of the genesis of tropical cyclones. However, where the index does not do very well is when we look at the temporal correlation. So here plotted are the curves of the number of tropical cyclone occurrences for the index, that's the blue curve, and then for the observed data, that's the orange curve. And we can see here that the correlation is very, very low. It's 0.27, just about, which obviously is not high enough to be able to do much with this. So in terms of the limitations of the index, this limitation of the poor temporal correlation is surely the most pressing one. But there's a couple of others. For example, the index was derived on a specific data set and is not, the values in the formula that we saw just before are not optimized in general. They're just derived empirically from data. And that goes for both the coefficients and exponents of the variables in the formula, as well as the pressure level at which the variables are taken. These were just derived empirically and not through optimization algorithms. So again, yeah, we see here all the values here, and these were derived empirically. So what we propose to do, instead of deriving the exponents empirically and then optimizing them to each data set that you want to calculate the index on, we propose to use a genetic algorithm, so a type of optimization algorithm, to find the most optimal arrangement and value for each of the components in the formula. To do so, we chose two objective functions. These are essentially goals that we're trying to either minimize or maximize. In our case, the two objective functions were the spatial correlation and the temporal correlation. In other words, we're asking the algorithm to maximize the correlation of those two variables by tweaking the various parameters in the equation. So we tested many thousands of potential combinations, all done under the hood by the optimization algorithm. And this yielded a Pareto Front of solutions. We'll see in a second what that is, but essentially that's a collection of potential formulas that have a trade-off in terms of the two components, so the spatial and temporal correlation. And we did our tests on two separate data sets just to be sure that we weren't overfitting on any single one. So this is the Pareto Front I was talking about. Here you see a series of black dots. Each dot corresponds to a different formulation of the genesis potential index, where the exponents are different. And you see that they all lie on kind of a curve here. And those express different trade-offs for the two objective functions, spatial correlation and temporal correlation. So you can choose one based on your preference on which variable you want to, which objective you want to optimize for. These were the results on the MERA2 dataset, and you can see the red dot here is the original configuration of the index. So every point to the right of it and above it is strictly better than the original version for both objective functions. And a similar plot for the other dataset that we tested on, the R5 dataset. Again, here each point is a different configuration of the index, and you can see that that here there's quite a few better versions of the index than were originally found by the authors. And if we take one, for example, this B1, just to inspect it a bit more in detail and see what has changed. A few things have changed that are notable. First of all, the exponents of the thermodynamic variables, those are the RH, that's relative humidity, and MPI, maximum potential intensity. the exponents of those two variables are much lower than they were in the original index. In the original version, they were both 3. Here they are 2.29 and 1.77. And indeed, we found that the index was trying to, or the optimization algorithm, sorry, was trying to lower these exponents in order to increase the temporal correlation. In other words, it seems like putting too much emphasis on these two variables is one of the reasons why the original version of the index doesn't perform quite as well in terms of temporal correlation. So that was the first very interesting finding. Second of all, as I highlighted here in green, the pressure level at which this specific variable, which is relative or absolute vorticity, was taken is 600 hectopascal. The value itself is not perhaps relevant to all of you who don't exactly know what this is, but what is relevant is that in the literature, most authors that we know of tend to pick this variable at 700 or 850 hectopascal. And the optimization algorithm for most of the solutions that we found suggested that this was a better pressure level at which to take this variable. So that was also an interesting finding that goes slightly against established common knowledge in the field. And then finally, we added a term here, an e to the power of 3, just about, that was suggested by previous research. A very recent paper from 1 or 2 years ago by Wang and Murakami suggested that adding this correction term normalized the equation slightly better. So we included that, and indeed, in all of the solutions that we found by the optimization algorithm, we found that having that extra term was helpful. So then visualizing the improvement that the proposed solution, this is relative to this specific solution here, we can see that the spatial correlation has increased, not dramatically, but still from 0.6 to 0.7, it's still a significant increase. And it represents the historical data slightly better. The one area in which the optimized index, similarly to the original index, though, doesn't perform very well is in this area, which we suspect might be because the index is maybe capturing other storms that are not tropical cyclones, whereas we're asking it to only capture tropical cyclones. And in terms of temporal correlation, also a pretty big improvement. What we're looking at here is an index that was optimized on the ERA5 dataset. And on the left, we use that same index on the ERA5 dataset, and we see that the temporal correlation has almost doubled. It was 0.20 something, 25. It almost doubled. So that's a pretty remarkable improvement. It is still only 0.43 though, so there is certainly still room for improvement. And then on the other data set, using the same index that was optimized on the other data set, the temporal correlation doesn't quite increase by as much, whereas when we were looking at the spatial correlation, that increased for both data sets. So in conclusion, findings from this work, solutions from one data set work well for the other. There should be an asterisk here saying in terms of spatial correlation, because in terms of temporal correlation, not so much. We found many equivalent solutions. This suggests that the problem may be over-parameterized in the sense that we might be missing some key underlying variable that explains the true variability of the genesis of tropical cyclones. This is enforced by the fact that the temporal correlation, although almost doubling, is still below where we would want it to be. So there might be something that we're missing in the formula, some variables that we might want to include on top of what we already have. Then that technical detail that I was reporting just before about the thermodynamic variables being, if not ignored, at least lowered in importance in the index. Absolute vorticity being taken at 600 hectopascal instead of 850, as is most frequent in the literature. yeah, these were the main findings. Then this work still is ongoing. There's still some open questions. First of all, in terms of next steps, we would like to repeat this analysis instead of at a global scale, at a local scale, or at least at a basin level scale, to understand if there are differences in each basin in terms of what variables are most conducive to tropical cyclone genesis. Then, as I was mentioning just now, there is a likelihood that some variables are missing from the index, and we would like to know if that's the case. And to do so, we might run some input variable selection algorithm to throw at the algorithm a bunch more input variables and see which one sticks, essentially. And then, as a last step, introduce some machine learning into the mix. Currently, this index is just purely a multiplication between a set of variables, but we would also like to explore the idea of using a machine learning algorithm as a stronger indicator of tropical cyclone genesis likelihood based on meteorological or climatological rather conditions. That's it from my side. Thank you very much.
Thank you very much, Guido. Thanks to both of you for very interesting and very clear talks on both an introduction to tropical cyclones and some of the modern state-of-the-art methods to detect them. I'm going to go straight to the Q&A and have a look at see how many questions we have. We have a few, so while we're answering these, I'll ask the rest of you to contribute to questions as well, because we have plenty of time for them. First question we have is from Marcello Milietta. So it says, "Hi Leone, the map of WMGPI shows a narrow band passing through the Mediterranean, where the index increases significantly. Which are the reasons of such a strong increase?"
Hi Marcello, thanks for the very good question. Yeah, it's true that the particular formulation of the index by Wang and Murakami shows a larger increase in future simulations in higher latitudes, in particular in the Mediterranean. I cannot give you a final and 100% proof answer because we haven't had time to look specifically at the Mediterranean yet. But I can comment a bit on the difference between this formulation of the index and the two other indices that I showed you before. So the difference of the Wang and Murakami formulation of the index is that it's built only upon the so-called dynamical variables. So they are variables related to the wind and in general to the circulation of the atmosphere. So they don't include the humidity, for example, that appears in the two other formulations of the index. But they include the vertical velocity, which is not present in the other two indices, as a proxy in a way of the convective activity. So even though I don't have a real answer to your question, I would imagine that this difference is somehow related to the variables that enter this index, and for sure it would be interesting to investigate this difference.
We have a question from Roberto, who actually says he had the same question as Marcello, plus, what about the distribution of those 80 to 90 tropical cyclones per year? Do all regions act equally, except for the South Atlantic? Any clue about the, I presume, that South Atlantic anomaly, e.g. possible correlation with other natural phenomena? Thanks for the webinar.
Yeah, should I? Okay. No, the distribution across the different ocean basins is not the same. It's actually highly different between one basin and the others. For example, the West-North Pacific has a very large number of tropical cyclones every year, while, for example, the North Indian Ocean has very few, one or two per year on average. And these these indices are able to explain some of those differences between different ocean basins. And in particular for the South Atlantic, what happens there is that there are a few cyclones that start to develop into the direction of a tropical cyclone, but normally they don't reach the threshold to be classified as tropical cyclones. They remain subtropical cyclones, except for a very few cases in the past. And the explanation that is normally given for this peculiarity about the South Atlantic is related to some of the quantities that have been described before. For example, the wind shear is normally very much higher over the South Atlantic with respect to other ocean basins. And also the SST anomalies are not that as high as in other ocean basins. So yeah, it's possible to relate this difference in the climatology to some of the factors that have been described by those indices.
Thank you, Leone. We have a shorter question here from Stella. Dear Leone and Guido, have you published these results? If yes, can you provide the reference? Guido, I think we saw one of the references in your slides.
Yes, and I believe it was the full reference, but yes, the optimization of the ENGPI has been published a couple of months ago in Environmental Research Communications. We also presented both my work and Leone's work at EGU last year. So there's an abstract for that as well. But yeah, I'll provide the reference. Do you want me, Ronan, to maybe put it on the slide and then share again the screen, or?
No, we can do private communication there, but Perfect. I will remind everyone that this is available on YouTube. The recording is available, so yeah, and we can go back and check as well. I'll move on to a question from Mutiala. Nice presentation, Guido. Is there any scientific reason to consider the 600 hectopascal vorticity? Is it different from basin to basin?
Great question. We don't know for certain. As I said, this is rather unusual in the literature to find this variable taken at this pressure level. A potential explanation, but I might refer to Leone if he has better intuition about this. But the potential explanation is that I believe we found a couple of papers that reported that in the structure of a tropical cyclone, the absolute vorticity peak is found at around 600 hectopascal. And so the algorithm choosing the variable at that height might be an indication of the algorithm trying to give more weight to this variable, essentially. So it's picking the variable where its value is the maximum to give it more importance in the formula. But we have this is our understanding. But we have not done the basin level analysis just yet, so we're not sure if this is the same for all basins, but we will verify that as a next step.
Leone, is there anything you want to add there?
No, basically I agree with what Guido said. Still work in progress, and we hope from the basin scale analysis to get some more also insight in the understanding of these physical mechanisms.
Okay. Very good. I'm glad to say we haven't finished yet with the questions. There's one here from Bronco. How come that the statistical indices tested, do not include any explicit air-sea interaction parameter? The SST was stated as crucial. Perhaps the ocean wave state is also important in the boundary layer interaction.
I can pick this one. So these indices were developed. The first one about 20 years ago, 20 years ago. And they were developed for large scale reanalysis and then applied to large scale climate models. So they were building upon some of these large scale parameters that those kind of models were able to reproduce well. And also the general idea of these indices was to relate the occurrence of cyclones to large scale parameters. For sure, yeah, Earth interaction is it's relevant, and there is some component of Earth interaction, even if not explicit. For example, in the original formulation of Emanuel and Nolan, the MPI somehow takes into account some aspects of Earth interaction, but yeah, I agree that these are important aspects, but this is an evolving, it's still an evolving field of study. So maybe it's possible that further formulations of the index will be proposed that include more parameters related to the boundary layer, especially now that we are reaching an era where the small scale information from both reanalysis and models is becoming much more precise.
Okay, we have one more here from Gabriella. Thank you for the very interesting presentations. This question is for Guido. What machine learning approach do you plan to use and for what task?
Excellent question. Well, specifically related to what we presented today, the idea of using machine learning was initially, but then it was somewhat discarded, to use convolutional neural networks. And the reasoning behind that was that we have spatially distributed maps. We have all this wonderful data and tons of it as well. So it made sense to use convolutional neural networks to essentially look at maps of these climatological variables and see if we could predict or estimate the likelihood of tropical cyclone formation. The problem there would be that although, yes, we have quite a bit of data, tropical cyclones are very rare. And that would mean that it would take some very precise tuning of the architecture to avoid the problem of data imbalance, because we would have many millions of grid points where no tropical cyclones even ever happened, and then very sparse points where they did. So that's one problem that you have to deal with if you want to do something like that. Alternatively, you could just take one grid cell instead of taking the whole map. You could take each grid cell separately and use a very shallow, very lightweight, simple neural network to basically do the same thing, estimate the likelihood of tropical cyclone formation in that grid cell. Somewhat addresses the problem of data imbalance, but not really. So that also has some problems associated with it. In the broader scope of the CLINT project, though, we are using machine learning also for other aspects of tropical cyclone analysis. For example, intensity estimation or studying the rainfall associated. So we're eager to bring some of that analysis also in this task.
We've come to the end of the questions on the chat. I'd like to throw in one or two, if I may. The first one, possibly for both of you, but based on some of the last results that Guido showed us on, I think, the improvement of spatial correlation and how you found that there was, if I'm correct, less improvement or none at all in the North Atlantic, and how that might be a sign of the algorithm confusing storms with tropical cyclones. If that's the case, why do we not see that signal, that contribution of confusion with storms in other ocean basins? And what can be done in the future to filter out the storms from the tropical cyclones?
Well, potentially that might be, first of all, that might not be at all why, like, what is happening. That's just an assumption, but potentially it's just a malfunctioning of the algorithm for other reasons that are currently not well known to us. But ideally, if following the next steps that I proposed towards the end of my presentation, if we found more explicative variables that truly captured the variability of tropical cyclones, then the assumption is that those would capture the genesis of only tropical cyclones, because in theory, those climatological conditions would be exclusively favorable for that type of storm. And therefore, an index that is optimized on those variables should, by default, filter out the other types of storms. For your other point, why we only see that, why don't we see that in all ocean basins? That I'm not quite sure. I don't know if Leone has any intuition about that, but yeah, that might point out to, again, not actually the algorithm capturing other storms, but in reality being just some false positives.
Leone, do you have anything to add there? Any ideas?
No, I mean, in general, no, just to add something on the detection algorithm. So well, that's more relevant for the modeling part, but of course, all these results are derived from the application of some detection algorithm of tropical cyclones, which, of course, they are as good as possible, but they are not 100% perfect. So it can happen a few times that they capture some other kind of storm that is not a tropical cyclone, but is something else in the same area. And so to avoid this, what we can do is to do some sensitivity studies, applying different detection algorithms, and improve the existing algorithms. But this is more related to the modeling part, where you need to first detect the cyclone themselves.
Okay, well, I think we've come to the end of all the questions then, and I thank everyone who did ask a question for very, very stimulating and interesting questions. The last comments there are thanking you both for very interesting presentations and congratulating you for the work. And I would second that, and I think they speak on behalf of everyone who's attended today. So the last thing I will do is thank you both again, Leone and Guido, for this very good seminar. Thanks to everyone else for attending. And a reminder that this recording will be available on YouTube in a couple of days. So everybody, thank you very much and goodbye.
Thank you, everyone.
Thank you. Bye.